Hi, I'm Martin Sweatman, and in this video I'm going to continue my review of the Younger Dryas Impact debate research. Now, so far we've covered the published research from the original Firestone et al. Paper in 2007 through to the middle of 2017 in the last video. And we've seen over this 10-year period of research how evidence in favour of a massive cosmic event at the Younger Dryas boundary is overwhelming. Especially, a platinum layer has been discovered in soil across North America at the base of the Younger Dryas black mat, which was predicted on the basis of a platinum spike in Greenland ice right at the onset to within a few years of the Younger Dryas cooling. And this platinum is found together with other impact proxies such as nanodiamonds and impact spherules that extend across 3 continents, indicating a truly massive event. So the case is very clear and compelling, and given that the coincident timing in the Greenland ice, as far as we can tell, between the platinum spike and the onset of cooling, and the scale of the event as well, it is almost certain the event actually triggered the Younger Dryas mini ice age. Only the effects of this dramatic event in terms of human population changes and megafaunal extinctions, and precisely how the impact triggered this cooling, is now really up for debate. Now, before we begin reviewing more papers from 2017, a bit of housework. Since I began my review of this Younger Dryas Impact bibliography, hosted by the Cosmic Tusk website back in October last year, it has been updated, and there are several new papers. Apart from the new papers published in 2019 and 2020 that we've yet to get to, there are also 4 new papers from earlier years that were previously omitted, and are now included. And here they are. And remember, I've hidden those entries that are just conference proceedings, non-refereed books and articles, or just opinion pieces in the Journal of Cosmology. Now, the 4 new entries are highlighted here with dark borders. Now, these additional papers make little difference to our story. We've gone far past them in the review, so far to 2017, and these papers occur in 2009 and 2010. But I do want to review them for completeness. So that's what I'm going to do in this video. Now, the paper by Carlson in 2010 is a critical response to the earlier paper by Mellott in the same journal. But we didn't review that paper because I thought it didn't have much to say about the impact theory. Turns out that was a mistake. So we'll need to properly review the Mellott et al. Paper first before considering the Carlson paper. Now, Mellott et al. Examine Greenland ice cores looking for the telltale signatures of a cosmic impact in terms of ammonium and nitrate ions and salts. Now, large volumes of these ions and their salts would have been created by the impact and both fallen out of the atmosphere directly or have been blown onto Greenland from distant lands by winds and storms over a much longer time scale. Now, the first thing to be aware of in this kind of work is that the atmospheric chemistry and resulting deposition of chemicals to Earth's surface caused by large cosmic impacts is really not that well understood. So this kind of study must be viewed cautiously. Nevertheless, there are some key processes involving the production of ammonium and nitrate ions by a cosmic impact that are expected. And as we have seen already, an abundance of ammonium ions is expected due to biomass burning. We saw that in the paper by Peteyev that revealed a platinum spike in the Greenland ice. However, this paper by Mellott et al. Suggests a couple of other mechanisms for ammonium ion production directly from the cosmic airburst, which we don't need to go into. But what about nitrates? We haven't mentioned these ions and their salts before. Well, when a large cosmic impact occurs, it creates extremely high temperatures in the explosion, and it's thought that this can cause nitrogen molecules in the atmosphere, and remember nitrogen exists as the diatomic molecule N2 in air, it causes this nitrogen to dissociate into highly reactive single nitrogen atoms. Now, because air is mostly nitrogen, it's about 78% nitrogen, 21% oxygen, and nearly 1% unreactive argon, we can expect a lot of these reactive nitrogen atoms to be created by the explosion. And they are expected to react with oxygen in the atmosphere to create various kinds of nitrous oxide, or NOx, including nitrates via several chemical pathways. So essentially the general view is that a cosmic impact will dissociate nitrogen in the atmosphere to form nitrates, whether it's in the form of nitric acid or metal nitrate salts or other forms of nitrate. Abundant nitrate ions should be there in the environment somewhere after a cosmic impact, it's thought. And provided there is a lot of biomass burning, so should ammonium ions. So Mellott et al. Look at 2 Greenland ice cores, and this is their data that you can see here, to see whether the ammonium and nitrate ions that we expect to find are really there. Now, this data is expressed on each plot here in terms of parts per billion versus years before present, BP. And remember, BP stands for before 1950 AD. Now on the left here is the data from the Grip ice core in Greenland, and you can see the data points are joined by these straight lines are very sparse every few hundred years or so. The middle plot is much higher resolution data from the GISP-2 ice core. Now these data points joined by lines are every 3 or 4 years. But the time scale here is much shorter. You see the Grip data here covers 3,000 years, whereas the GISP-2 data only covers 500 years. Now on the right we also have data from the GISP-2 ice core, but this time sampled with a resolution that looks to be less than 1 month. The vertical axis is the same in each case, parts per billion, from 0 to 200. So we can compare these plots directly. But notice the dates here. These peaks here correspond to the Tunguska impact in Siberia in 1908. So Mellott's aim then is to compare the nitrate and ammonium signals in these ice cores for the Tunguska impact in 1908 AD and the Younger Dryas impact roughly 10,835 BC. Now, of course, the Tunguska impact was much smaller, and the type of impactor is not known exactly, but probably it was a chunk of comet. And so according to Mellott et al., this signal from Tunguska should be around 1 million times smaller than the Younger Dryas impact signal. Now, their estimate here, that the Younger Dryas event was 1 million times larger, or at least 1 million times more energetic than the Tunguska event, is, in my view, an overestimate. If the Tunguska impactor was 100 meters in diameter, which is often quoted, then their estimate suggests the Younger Dryas impactor was 10 kilometers in diameter, and nobody is suggesting such a large impactor for the Younger Dryas event, I don't think. More likely, I think, the Younger Dryas event was in the region of, say, 1,000 to 100,000 times larger than the Tunguska event. Whatever, it's expected to be at least several orders of magnitude larger. Now, the first thing to note about this data is that the timing of the onset of the Younger Dryas period is different in the Grip and the GISP-2 ice cores. And this offset is known to be caused by miscounting ice layers. But that offset is not known with great accuracy. So Mellott et al. Don't really know whether this ammonium spike evident in the Grip data corresponds to this ammonium spike in the GISP-2 data, or this one, or this one, or this one, or in fact all of them, with all these spikes perhaps caused by ammonium ions being blown into the Greenland ice by ice storms. So that's the first problem with this data. And here's another problem. See the ammonium peak here in the GRIP-2, in the Grip data. Its width is about well, let's say 500 years, which means this entire data series in the GISP2 data could be indicating an excess of ammonium ions. But because this time axis is only 500 years long, we can't see whether this is an excess of the ammonium ions in the GISP2 data. Basically, this GISP2 data series needs to be much longer so that we can make that comparison with this data series and this data series. In fact, the situation is even worse than that for the nitrate data. So here in the GRIP data, we seem to have an excess of nitrate lasting around 1,000 years, practically the whole of the Younger Dryas period. So we can't know how much of this apparent excess nitrate signal is caused by a cosmic impact or simply by a change in climate during the Younger Dryas, or both perhaps. Moreover, this time span of 1,000 years is much longer than the time span of this GISP2 data series, which is only 500 years. So we can't know if this entire GISP2 data series is representing an excess of nitrate or not. The next problem with this data is that nitrate and ammonium ions in the atmosphere are expected to only last a few months to a few years, depending on their height in the atmosphere and the prevailing weather. But this is really uncertain because the details of the atmospheric chemistry and the lifetime of various ions and aerosols in the atmosphere is quite uncertain. Nevertheless, it's normally expected these signals will last no more than a few years if they have a direct atmospheric origin. And this is clearly the case for the Tunguska impact, where both signals last only about 2 months. But when we look at the Younger Dryas event signals in the GRIP data, it seems they last hundreds or even thousands of years. So it seems that neither of these Younger Dryas event signals in the GRIP data could have been produced directly by atmospheric fallout. Instead, the GRIP data is probably showing us the much longer duration signal corresponding to wind-blown dust carrying ammonium and nitrate ions remaining in the environment after the impact onto Greenland. So there are real problems in analysing and comparing this data between the GRIP and GISP2 ice cores. And in my view, this undermines this whole paper. But that's not a problem noted by Merlot et al. They are content with identifying this single tiny peak as the entire nitrate signal created by the Younger Dryas impact, and this single tiny peak as the entire ammonium signal. And I have real problems with that. I don't think that can be right. Nevertheless, that's their assumption. Now, the problem observed by Merlot et al. Is that when they compare this specific spike in the GISP2 data with the ones caused by the Tunguska impact event in 1908, they are almost the same height. And given that the Younger Dryas event is expected to be at least 1,000 and maybe as much as 100,000 times larger, this suggests there's a lot of missing ammonium and nitrate in the GISP2 signal. And this is their conclusion. In fact, they suggest the nitrate signal in particular has been undersampled. In other words, they suggest that the real nitrate signal might lie between the sampling points in the GISP2 ice core. Now, I agree that seems quite likely and it should be investigated. A lot would depend on how the GISP2 measurements were made and what was the GISP2 ice core sampling strategy. I don't know. We'd need to look closely at the details of those papers. However, I think a more important point was missed by Merlot et al. And that is that when we compare the Tunguska and GRIP data, they are reasonably compatible. The GRIP signals last for hundreds or thousands of years. Therefore, the total excess nitrogen and ammonium signals, when we add them up over those long time periods, do compare quite well with the much shorter Tunguska signals. But there is a lot of uncertainty here because we don't know how much of this excess nitrate signal over the whole of the GRIP data series is caused simply by climate change and how much can be attributed to the cosmic impact. So in the end, there's a scientific mystery here. On the one hand, if we take the GRIP and GISP2 data at face value, it seems they are missing huge nitrate and ammonium peaks corresponding to the atmospheric fallout of these ions. And possibly this is explained by undersampling the ice cores. The Tunguska data shows us these signals are only expected to last a few months, so the signals are only a few months wide. So they could easily be missed by measurements every 3 or 4 years in the GISP2 data, or every few hundred years in the case of the GRIP data. In the end, I don't see this as a serious problem for the impact theory. It seems likely to me that at least some of this extended nitrate ion signal and most of the ammonium signal apparent in the GRIP data is caused by the impact. So in the end, all we're missing are the strong peaks due to direct atmospheric fallout, which have likely been undersampled or missed by the sampling strategy. Okay, given all that uncertainty, we can now put the comments by Carlson in his response in context. He agrees that the GISP2 nitrate signal especially looks to be inconsistent with a Younger Dryas impact event, considering that it's generally thought the nitrate signal should be a single narrow spike lasting at most a few years, and therefore it should be very, very high and prominent, and it isn't there in the GISP2 data. But he doesn't comment on the GRIP signal, which appears to show, like the ammonium signal, an extended nitrate signal that lasts for 1,000 years or more. He agrees this discrepancy might be caused by undersampling the GISP2 ice core. He also points to other problems with the Younger Dryas impact, but none of these are significant, and we've already dealt with most of them. So the mystery of the confusing nitrate signal especially remains. Okay, now let's consider the paper by Steele in 2010. Remember the earlier paper by Holliday and Meltzer that suggested that there was no change in the human population of North America after the Younger Dryas event. But it was clear from analysis of their own data, which was simply a table of radiocarbon dates of all ancient campsites found close to the time of the Younger Dryas event, that they were wrong. And here we are. This is Holliday and Meltzer's key data that we reviewed back in video 2. So they were looking for a break in the occupation. They were looking for a clear gap in the timing of these ancient campsites, and ignored the change in slope at around 10,800 BC apparent in this data. Well, Steele reanalyzes the database of radiocarbon dates behind this archaeological data and finds that the conclusions depend on which radiocarbon calibration curve you use. So here is his main result. So these plots essentially reveal the likely human population density in North America at the time of the Younger Dryas event. Now it's clear that when we use the INT-Cal 04 calibration, there appears to be a dramatic drop in population right after the onset of the Younger Dryas period, which begins about here. But when we use the later calibration curve from 2009, INT-Cal 09, that dramatic drop has been flattened and moved forward by around 200 years. So it now appears to be inconsistent with the impact theory. But these plots don't include the uncertainty in the data, and much of that uncertainty comes from the 2009 calibration curve. So we still can't make any clear conclusions on this basis. Here we go. This is what I mean. So here I've plotted the actual calibration curves for the INT-Cal 09, that's the green curves, and the improved and more recent INT-Cal 13 curves, that's the red ones, just to give you an idea of what I'm talking about. And what they show is that if you have a radiocarbon date that is exactly 11,000 years BP with no uncertainty, then that equates to date ranges of about 10,700 BC to 11,100 BC using the 2009 curve, while it is about 10,800 to 11,000 BC using the 2013 calibration curve, and that's with 90% confidence, or 2 times the standard error, which is represented by the gap in these lines. The point is, it's difficult to resolve the question of whether there was a population collapse after the Younger Dryas event using calibrated radiocarbon data, especially if you're using the 2009 calibration curve, where there's quite a lot of uncertainty exactly around the Younger Dryas event. In fact, Steele agrees with this. He says later in the paper that the evidence reanalyzed in this paper is equivocal, meaning it's uncertain, because of the very significant changes introduced in the new INTCAL 09 calibration curve for this period around the Younger Dryas event. And then later in his conclusions he says that the archaeological data needs to be screened and processed using appropriate statistical and stratigraphic criteria, particularly if we are exploring a hypothesis of an abrupt and relatively short-lived extreme event. And now that we can definitively locate the Younger Dryas boundary using the platinum anomaly discovered in 2017, and remember Steele didn't know about that at the time in 2010, that task, the relating the archaeological data stratigraphically, that task is made much easier. Basically what's needed in future are studies that compare the stratigraphic position of archaeological finds like Clovis tools with this platinum signal. It's the only way to answer this question. It can't be done through calibrated radiocarbon data. So the issue remains unsolved by Steele's paper. Now let's move on to this paper by Kaiser et al. In 2009. So they analysed the Ursulo horizon, which is the European equivalent of the Younger Dryas boundary, at nearly 40 sites across northwestern Europe. And they argue on the basis of individual radiocarbon measurements and pairs of optically stimulated luminescence measurements at each site that this layer in the sediment, this Ursulo horizon, that it developed at different times in different places, and this therefore contradicts the Younger Dryas impact theory, which requires synchronicity. However, we should first note that the Younger Dryas boundary is signalled by geochemical markers like nanodiamonds, impact spherules and platinum, and so radiocarbon dating or optically stimulated luminescence dating a darker sediment layer cannot be used by itself to contradict the theory. Moreover, even if we assume the darker sediment layer does mark the Younger Dryas event, these authors also make a basic error in equating the variability in the radiocarbon dates obtained for it with the variability in the formation date of it. In other words, they misunderstand the experimental uncertainty in their data. So here is their radiocarbon data. This is figure A, taken from charcoal samples within the black sediment layer from each of the sites, which are given these acronyms on the top here. And I've drawn on top of this figure the range of dates for the Younger Dryas event from the 2015 paper by the Comet Research Group, and that's this thick blue line here. And I've moved it back by about 100 years to take account of the older 2004 calibration curve that these authors are using compared to the Comet Research Group in 2015. Now it's clear from this that most of their radiocarbon dates for this Ursulo horizon at the different sites that they analyse are consistent within the uncertainty of their measurements with this thick blue line. A few of the radiocarbon dates, like this one here or this one here, are consistent at the level of 3 sigma, or 3 times the length of these error bars, which is what you'd expect for nearly 20 different data points. Now the only radiocarbon data in this set that looks to be inconsistent with this being a synchronous event are these 2 measurements here. They are within 4 to 5 sigma, which is a little bit too much for these less than 20 data points. So apart from these 2 outliers, this data is consistent with the impact hypothesis. Now let's look at their optically stimulated luminescence data in figure B below. And it's the same story. These measurements are taken from quartz crystals above and below the charcoal layer at each site. So we are looking for the open circles to be above this thick blue line, which represents the Younger Dryas event, and the filled circles to be below it. And you can easily see that when we take into account the error bars or uncertainty in these measurements, this is always the case in every single measurement. So their conclusion that this data contradicts the impact theory is not supported. Should we be worried about these two outliers in the radiocarbon data? Well, not especially. You see, all of these data points correspond to single measurements. And we know that proper age depth models require many radiocarbon measurements from a range of soil depths, because the uncertainty in single radiocarbon measurements rarely represents the true uncertainty or the scatter in the data. In fact, moving on, the next work illustrates this point nicely. Now we're going to review the paper by Gillett et al. From 2009. So this illustrates that we can expect the true uncertainty in radiocarbon dating of sediments to be greater than from a single measurement. Now, these researchers looked at sediments from the bottom of a small lake, a small Paleolithic lake in North America, and from that they extrapolated their results to the whole of the North American continent. They were looking for fungal spores that concentrate in animal dung and then get washed into rivers and lakes. And by measuring the concentration of these spores with depth in the sediments at the bottom of this lake, they reconstructed the megafaunal population across the Younger Dryas period. And by the way, this paper is from the journal Science, so it's one of the most prestigious journals there is. So this paper is going to be really good with tough peer reviews to make sure its conclusions are supported by their data, right? Well, let's see. So their main conclusion is that the megafauna around this lake, and by extension the rest of North America, began declining thousands of years before any potential cosmic impact event. And here is their data from the lake sediment core that they claim supports this conclusion. Now, it shows how various types of pollen in these 6 plots here, it shows how they change with time on this axis. The megafaunal population, represented by the concentration of fungal spores in the lake sediments, is plotted here in blue. This plot here shows how dissimilar the vegetation was compared with modern plant types, how that changed with time, and finally in black we have a plot of the charcoal abundance with depth, and therefore with time in the lake sediments. Now, just by inspection and ignoring their dating, which we'll look at in a moment, I would expect that this charcoal peak corresponds to the Younger Dryas event, because when we look at the overall difference in the vegetation, we see that we have around about a 1300 year bump in this data just after this charcoal peak. So I expect this bump corresponds to the return of the Ice Age, the Younger Dryas Ice Age, and this charcoal bump represents the onset of those conditions. And also, this change in the vegetation correlates nicely with dramatic changes in the amount of beech and ash, that's these 2 types of pollen, in the lake sediments. And moreover, until this point, you could argue that the megafauna, represented by this blue plot, were fairly reasonably constant up until around about here, exactly when this charcoal bump appears. So up until this point, you could say that the megafauna, although there was a lot of variation, were more or less constant. And then we have the charcoal or the Younger Dryas event, and then there's this die-off, this quick die-off in the megafaunal population. However, the problem is, according to their dating, this charcoal peak occurs around 12,200 BC, which is over 1,000 years earlier than the Younger Dryas event, and there's no error or uncertainty recorded in their timeline or in their conclusions, so this must be an accurate timeline, right? Well, let's see how they created this timeline. We have to go to their supplementary information to do that. Here it is. So of course their timeline is reconstructed using radiocarbon data from their sediment core, and here is the original radiocarbon data. Now it's immediately apparent that there's a lot of uncertainty in the radiocarbon dating of this sediment core. I mean huge uncertainty. So we can know straight away that their conclusions are unsupportable. So let's see what they actually did to obtain their timeline. Well, first they eliminated a couple of data points that they considered to be anomalous. So they got rid of this point labeled C and these orange points labeled B. And with the remaining data, they then construct a linear or straight line fit, which is fine, but they neglect to even discuss the remaining uncertainty in this fit in their conclusions. Now clearly, in this straight line fit, this end of the line seems to be well constrained by these two data points, but its slope is hugely uncertain because of these data points. In fact, even their assumption of a straight line fit can be questioned. So, for example, after the impact event, we can expect a significant additional water runoff due to severe storms. And therefore there is no way of knowing whether a single straight line is the best way to represent the age depth model for this lake. Now, I'm not saying the authors should have tried other types of fit, curved lines for example. The data is too scattered to know what type of fit is best. What I'm saying is that their conclusions should have been tempered by this experimental uncertainty, which looks to be in the region of about 1,000 years. But unfortunately it wasn't. Now it's quite clear that there is a strong argument actually that their data supports the impact hypothesis as triggering the North American megafaunal extinction, completely opposite to their conclusions. You know, this paper really annoys me. Even though it's published in what is supposed to be a top scientific journal, its data analysis is completely rubbish. Not only do they neglect the uncertainty in their radiocarbon data, but they neglect this clue in their own pollen data and charcoal data that should have hinted they might be making an unsupportable conclusion, perhaps even a completely wrong conclusion. It's some of the worst science I've seen in this whole saga. This is a massive failure in peer review standards for this journal. I mean, look, the Younger Dryas was a mini ice age, so North American climate changed dramatically and very suddenly at its onset. And yet, according to their timeline, at 12,800 years BC, there is no significant change in any of their data sets at this time. It's nonsensical. And at the very least, the peer reviewers should have picked this up. It's completely obvious that probably this charcoal signal corresponds to the Younger Dryas event. It seems to me once again that the authors were desperate to reach a predetermined conclusion, and the peer reviewers were only too happy to help them. Alright, having reviewed these 4 earlier papers, we'll move back to the research published in the rest of 2017 in the next video. What we learned from these 4 papers is that the story is relatively unchanged, although the expected massive nitrate and ammonium signals in the Greenland ice cores seem to be missing. Probably they've been undersampled. And once again, we see that many scientists have problems in understanding the uncertainty in their data, especially if it suits them. Okay, if you enjoyed that, then please take a look at my book and my blog.